Here is retrosynthetic analysis followed by forward synthesis of an aldehyde. I will go ahead and label the carbon atoms of this aldehyde just to keep track of them. And I will think about the immediate precursor to an aldehyde. Precursor to carbonyls such as ketone and aldehyde is always an enol. En being an alkene and ol being the alcohol. So in this case, my en part, my en portion, the double bond in the precursor will be between carbons 1 and 2, and my OH of the ol part, the alcohol, will be on the same carbon where the carbonyl oxygen now resides, on carbon number 1. So I will go ahead and draw retrosynthetic arrow and draw the structure of my immediate precursor to this aldehyde. So cyclohexyl, carbons 3, 2, and 1. Double bond is now between carbons 1 and 2. And the alcohol is on carbon number 1. So here is my enol tautomer, an intermediate which will spontaneously tautomerize going forward to the product aldehyde. And I will label it as B. Thinking about the precursor to an enol, I think about a triple bond. So what I have here at the enol, I have a hydrogen and a hydrogen. So going backwards in a retrosynthetic sense, we have a terminal alkyne with a triple bond between carbons 1 and 2. So carbon 3, 2, and 1. And the precursor to a terminal alkyne is an acetylene, which will give us carbons 1 and 2. And the remaining portion of the alkyne C will be an alkyl halide. So carbon number 3 attached to a leaving group such as bromide or iodide. And we'll designate it as an RX, our alkylating agent. So now we finish retrosynthetic analysis and we can go ahead and show forward synthesis. Starting with acetylene, we'll carry out chain extension reaction. It's a two-step reaction which involves addition of a strong base, sodium amide, in anhydrous liquid ammonia. Step 1 serves to affect deprotonation of one of the hydrogen atoms from acetylene. And once we form acetylide in situ, it will attack the electrophile, our alkyl halide, leading to chain extension. So the second step is the bond forming, carbon-carbon bond forming reaction, whereas the first step is deprotonation. So chain will be extended on the left-hand side of the acetylene to give us alkyne C. Let's now think going forward from C to B. How can we affect this transformation? What is happening from C to B is addition of water across the triple bond, which is a hydration reaction. Hydration means addition of water. So I will designate the two carbons of the acetylene as primary carbon and a secondary carbon. And now I'm looking at my enol and I'm trying to decide whether the hydration proceeded in a Markovnikov or non-Markovnikov fashion. I see that the OH added to the less highly substituted carbon, whereas the hydrogen added to the more highly substituted secondary carbon, indicating a non-Markovnikov orientation of hydration. So I need non-Markovnikov conditions, which is a two-step reaction, addition of organoborane R2BH or BH3 in THF, followed by oxidation using hydrogen peroxide as the oxidizing agent under basic conditions. So we need some kind of base in aqueous medium so that the base will dissolve. This will give me enol tautomer B, and this intermediate will spontaneously tautomerize, spontaneous tautomerization to the corresponding carbonyl, which in our case is the aldehyde. And this equilibrium lies heavily on the side of the carbonyl.